Hey everyone, and welcome back. We are into Unit 4 of Geometry, which is our Similarity unit. The previous unit was quadrilaterals, and we just finished wrapping that up. So let's take a look at what we're going to be covering today. All right, so in this unit, we are going to look at what is the definition of similarity. We're going to look at some properties of dilation. So we're going to focus on this transformation that we didn't use back in our transformation section. So it's called a dilation, and the other ones we did were translations, rotations, and reflections. So this is the fourth type of transformation that we can do, along with stretches and compressions, which you saw in Algebra 1. So that kind of rounds out the things that we can do to a shape. So we're going to dig into that a little bit more today. And we're going to look at scale factors. So what is this? How does it work? How do we determine it? And so on. Questions for today. What is a dilation, and what does it mean if shapes are similar? How can I tell if a dilation is making a shape larger or smaller? And how do I determine scale factor? Okay, we're going to start with a warm-up question. This is what a unit test or a benchmark question might look like for similarity, and it actually kind of involves quadrilaterals as well. So they kind of form a hybrid question. We saw like parts A and B maybe in the quadrilaterals unit, but C and D are something a little bit new. So let's recap. From points A and B, they form one side of a square. We want to complete the square to find points C and D, and we're told that point D is of the form 0, y. So that means the x-coordinate is 0, the y-coordinate is unknown. Now, if the x-coordinate is 0, what does that mean? Think about it now before we get to the question. Part B, find the perimeter and area of the original shape ABCD. Part C, so now we're going to come back to coordinate transformation. So we've seen this setup before. Put the shape through the following transformations. XY then becomes minus YX, which becomes a half X, a half Y. So what are those transformations? What are they going to do to the shape? And then part D, what is the relationship between the area and the perimeter of the original shape and the images, perimeter and area? So we're going to compare the two of those when we're done. Okay, so first part, we saw this in the last unit, should be pretty kind of easy for us to do. Points A and B, let's put those on a coordinate plane, see where they are. And then we know there are two possible squares we can do from this. So we've got the square that, I'm just going to kind of sketch it in roughly. So the square that will be going up top, and then also the one that will be going down to the bottom. We have to figure out which one we actually want in this case. So the thing we're told is that the point D is of the form 0y. So that means D is going to have an x-coordinate of 0, which means it's going to be on the y-axis. Because remember, x-coordinate of 0 means we're moving right, left, 0 units. So it's going to be on that vertical y-axis. So if that is the case, it wouldn't really be possible, because A is going to connect to D. It wouldn't be possible for D to be down here somewhere. So that means we must be going up and to the right. So our square is going to be above AB. So how do we do that? Let's think about it. Pause the video, go find points C and D. Okay, so let's just draw in AB with a relatively straight line. So for me, that is down 2 units and right 4. So AB, the slope is minus 2 over 4. And I'm actually not going to simplify it here, because we realized in the quadrilaterals unit that for doing squares, if I leave it in that unsimplified form, I can use it for locating the other points. Because we know BC is going to have a perpendicular slope to this, so minus 2 over 4 is going to be perpendicular. Flip it and change the sign. So minus 4 over minus 2, which simplifies to be positive 4 over 2. And again, not simplifying it, because that means we're going to go up 4 and right 2. So by not simplifying it, I get to keep the side lengths the same as well. It's over 2 of 4. C is located at 4, 6. If I do the exact same thing for AD, so Remember, order of a shape is A, B, C, D. So A connects to B, B to C, C to D, and then D comes back and connects to A to close the shape off. So we know AD is going to have the same slope as BC. So I'm going to count over 2, up 4. So D is at 0, 8. So my square is going to be right here. So D, 0, 8. So there's our 2 points that answers this part. So keep those numbers written down somewhere. Remember them for later. We're going to need them. Part B, find the perimeter and area of the original shape, so ABCD. Now to do this, because it's a square, we only really need to find the length of one side, and then we can apply our area and perimeter formulas. So since A and B are given to us, let's just figure out the length of AB. So if you remember from the last slide, when we did our right angle triangles, we figured out slope, it was down 2 and right 4. So that's our right angle triangle. So forget the negative, it's just 2 units. So it's going to be 2 squared plus 4 squared. And we're going to square root that whole thing to get the length of AB. So that's going to be the square root of 2 squared is 4 plus 16. So that's going to be root 20 is equal to AB. So now at this point, area of a square is equal to the width squared. So this is going to be square root of 20 squared. Now what happens when you square a square root number? A little bit of a tongue twister there. They are the inverse operations for each other. So squaring something and square rooting will cancel each other out. We will end up with 20 units squared for the area. The perimeter, on the other hand, property of a square, we know all sides are congruent. There are 4 sides in a square, so it's going to be 4 times the square root of 20. So if we were leaving this in like radical form, we would say it's 4 root 20, but we'll put it in our calculator, we'll round just to get an actual definite answer. So 4 times square root of 20 is 17.888. And there's a 5 after that. Round to the nearest hundredth, 17.89. And that's just single units. All right, so again, hold those numbers in your head somewhere, write them down. So I'm just going to write them on a little piece of paper here for myself, and moving on. Part C. Put the shape through the transformation. I wrote down our coordinates so that we can use those again. Remember how this works. X, Y is your original point. We put it through this transformation. Can you guys remember what this transformation is? So you've got a negative yx. What type of transformation was that? So hopefully you're remembering that is a rotation of 90 degrees. And then is it going clockwise or counterclockwise? That's always the question. So if the original y value was positive, it becomes negative. The negative x, it is rotating 90 degrees counterclockwise. So this is the original. This is the pre-image. And then this last transformation, half x, half y, we are multiplying the coordinates by something. So that is going to be a dilation. So we will get into kind of some of these terms a little bit later, but essentially the half is what we call our scale factor. So this is what we are multiplying our coordinates by. All right, so we have to put the points of the shape through this transformation. So we've got A is minus 2, 4. That first transformation, we're going to reverse x and y and change the sign of y. So it's going to become minus 4, minus 2. And then we're going to divide both numbers by 2 or multiply by half. So it's going to be minus 2, minus 1. And that is the coordinate of a double prime because it's gone through 2 transformations. B is at 2, 2. So switch them, change the sign, -2, +2, multiply by half, -1, 1, and that's B double prime. And then C, 4, 6. So it'll be -6, 4, -3, 2 is going to be C double prime. And then last but not least, D is 0, 8. So that's -8, 0. And that'll be -4. And then 0 divided by 2, or 0 times a half is still 0. And that's D double prime. All right, so those would be our 4 points. If you plotted that on the coordinate plane, what you would notice is that the shape has rotated 90 degrees, and it's also half of the size that it originally was, so half the side lengths. All right, so for part D, what is the relationship between the area and the perimeter of the original shape? And the image is perimeter and area. So let's think about the original shape, the pre-image. Image. Apologies for the writing again. So our pre-image had an area of 20 units squared. And the perimeter was 4 times root 20, or when we rounded it, it was 17.89. And that was just standard units. So now let's talk about the image. From our previous work, I'm just going to bring over point A double prime. So that was -2, -1. And B double prime, -1, 1. So it's still a square. We saw that from the, if we plotted the point, you'd see it was still a square. If we checked the properties, it would still be a square. So let's have a look at now the length from A double prime to B double prime. So we've got distance. So x2 minus x1 squared plus y2 minus y1 squared. And this is the same thing as Pythagoras' theorem. It's just I don't have it on a graph, so I'm going to put it in here and do it this way for this one. So distance, this will be x1, y1, x2, y2, square roots. So we got x2 minus 1 minus -2. So we're going to have that double negative situation. Make sure we keep an eye out for that. Plus y2 is 1, and then minus another double negative situation. So we're going to have a plus out here and a plus up here. So this will be square root of -1 plus 2, which is just 1 squared. And -1 plus 1 is 2 squared. So that's going to be square root of 5. Okay, so square root of 5 is going to be the length of one side. Area is going to equal square root of 5 squared, which we saw from earlier. They just cancel, and we get 5 units. And then perimeter is going to be 4 times the square root of 5. And if we type that in, 4 times square root of 5, we get 8.99. Or sorry, 8.94. And 427. Okay, units. So now the last part is, how do they compare? Now you would have thought, oh, we did a scale factor of 1/2, so we divide everything in 2. The area should be half of the original area, but 5 is not half of 20. It's actually a quarter of it. So the area, so we're going to kind of summarize this, area is 1/4 of original. But when we look at the perimeter, if you took 4 root 20 and divided by 4 root 5, you'll get 2. So actually the perimeter is half. So like if we didn't do any rounding, and like you can see, like if you double this, it'd be 16, 17.9, and then 9, or sorry, 8, and then 8.8, 8.9. So like it's about halfway. It's actually exactly if we didn't round. Perimeter is half of a ridge. So now that presents an interesting situation. Why is the area one fraction of the total, but the perimeter is a different fraction, even though we put everything through the same scale factor? That's going to be a question we want to try and answer today. Okay, so what is a dilation? A dilation is a transformation that changes the size. So the shape's going to stay the exact same, the properties of the shape will stay the same, but it's going to get bigger or smaller. So we have key parts are a center of dilation. So this is where all points are moving from or towards, and then a scale factor, which is going to determine like how much bigger, how much smaller are we going to make these things. A stretch, on the other hand, is something you saw in Algebra 1. You will see it in Algebra 2 as well. We do it with functions a lot, and that's where you are multiplying the x and y coordinates by something, but they're not the same value. So say like you said, all right, I'm going to multiply the x coordinate by 5, but I'm going to multiply the y coordinate by a half. You would end up with a stretch. So the x and y dimensions are not increasing or decreasing by the same percentage amount. Okay, so let's go back to our situation here where the scale factor was a half. The blue square is the original. The red square is the image. So now what we notice is that the side lengths are half. So like if I move squares into position, each square side length is half of the blue one, but there's 4 of those squares in the actual blue square. So just like once, like when we think about it, if we did the half and the half on each side, so here is one of my squares, the area is only a quarter of the original square. So now when we look at that, scale factor is a half, the area is going to be a half squared. So actually what happens is you take the scale factor, and for area you're going to square the scale factor, and that is essentially the factor of how the area is going to change. So if the scale factor had been, say, like 3, you would have said, all right, the perimeter will change by 3, so you multiply the perimeter by 3, but the area will change by 3 squared, so the area would actually be 9 times the original shape. So when you think about that, like if we started with 1 square and then you multiply by 3, so now it's 3 long and 3 high, well now you would have 9 of those little squares. So that's kind of the visual that we see. Bonus points if you can tell me what happens when we go 3D and we cube something. So say we had one little cube and we do a scale factor of 3. Well, now you've got 3 across the bottom on either side, plus you're now going up 3 on each one. And excuse my really bad drawing, but imagine a Rubik's Cube. So a 3 by 3 by 3 box. So there would be 9 cubes per row, and there's 3 rows. So you would actually end up with 27. So for volume, so we'll see volume much later, volume is actually the scale factor represented by letter K, cube. So that becomes your volume factor. So just to recap, perimeter will change by the scale factor. Area will change by the scale factor squared, and volume will be scale factor cubed. So that's the kind of shortcut we need to remember. All right, so properties of dilations. We saw this when we did our other transformations. So in rotations, reflections, and translations, the pre-image and the image, so the original and the copy, were completely identical. Nothing changed. So they had all the same properties, all the same angles, the side lengths were the same, everything was the same. In a dilation, it's almost the same. This is what we call a similarity transformation. So the image is going to be similar to the pre-image. Now, what does that mean? It means that the angles are going to be the same, so preserves angle measurement. The dilation preserves betweenness, so if points are between other ones, or they're inside of the shape versus outside, all that's going to stay the same. If points were collinear in the beginning, they will be collinear in the image. So if we had A, B, C on the same line, they will A prime, B prime, C prime will still be on the same line in an image from a dilation. So this is something a little bit different now. A dilation maps a line not passing through the center of dilation to a parallel line and leaves a line passing through the center of dilation unchanged. So we'll see kind of an image of a picture of that in a couple of seconds. So keep a pin on that one for if you have questions about it. And then the dilation of a line segment is longer or shorter by the given scale factor. So like if we are doing a scale factor of a half, the image will be half of the original. If it's a third, the image length will be a third of the original, and so on. All right, so center of dilation, what is it? Definition, point at which all points of the shape are moving towards or away from by that given scale factor. So what you'll notice is in real life, where you see dilations, your pupils dilate. So the open space inside of your iris, the iris is the color part of your eye, that the iris contracts or expands to allow more or less light into your eye, and the center of dilation would be at the very center of your pupil, so the dark appearing spot of your eye. If you're thinking about zooming in on a picture on, say, like your phone, phones are programs that when you put two fingers on the screen, it finds the midpoint between your two fingers, and that it becomes the center of dilation. So as you move your fingers away from each other, the picture expands. As you move them closer together, the picture shrinks towards that center of dilation. So like it's not like you're stretching the photo, it will always just expand or contract with all dimensions the exact same scale factor. So scale factor, the ratio at which the distance from the center of dilation increases or decreases, or how the side lengths increase or decrease. All right, on a coordinate plane, when we are doing dilations, unless you're told otherwise, the center of dilation is going to be at 0, 0. So we can say, all right, we're going to do a dilation from center dilation at 3, 5. So pick a random coordinate. But if you're not told anything, the default is 0, 0. Kind of like with rotations, the default is go counterclockwise, or with like reflections, we reflect over one of the X or Y axis typically, unless we were told otherwise. So like that's the default you're going to go with. Scale factor represented by letter K, and on coordinates, we do dilations by multiplying by X and Y. So that, remember, reminds you of kind of like rotations, where if we flip the X and Y coordinate and then multiply one of them by -1, so we caused a rotation. For reflections, we just changed the sign on one of the coordinates. For dilations, we're going to multiply, and then translations was add or subtract. All right, so this would be another practice opportunity for you. Here are the points A, B, C, D, E. Put them on a piece of graph paper. Do a dilation with a scale factor of 5/2. So as a decimal, that will be 2.5 or 2.5. So what we do is we say, okay, here's my original points. Multiply the X and Y coordinates by 5/2. So here's what your new coordinates should look like. So on a coordinate plane, you would notice that it got quite large, like 2.5 times the size is quite a big dilation. It will get quite big. So make sure you gave yourself plenty of space. All right, so next up, we're going to do an activity. Now this one's a little bit more challenging because you're going to have to do this on your own versus in a class where we could chat about it, but I think you'll be able to figure it out. So it's a Geogebra applet. So this is like a Geogebra sheet in which like there's very fixed things that you can do with it. And then you're going to manipulate that applet to answer questions about dilations. So here's the questions I'm going to ask you to answer. You will do all of this in the assignment on Schoology. So make sure you are not just like writing these down or answering them in your head. These are going to go into an assignment on Schoology. So it's a Google Doc. You're going to type in your answers. So again, questions already written for you, and I want 1 to 2 sentences per answer. So what happens when the scale factor is less than 0? So describe what you see. What happens to the shape? Think about side lengths, angles, position. What is the scale factor, or at what scale factor does the shape start to grow? So at which point does the size of the shape start to get larger? Again, experiment, look and see what is that exact point. What happens when the scale factor is -1? Describe what's happening. Again, thinking angles, side lengths, orientation, position, other transformations that maybe have come into play. What happens if the center of dilation is inside of the pre-image? So you will have the ability to pick up and move the center of dilation, move it, and see, okay, what happens if I put it inside the shape? What happens if it's outside? What happens if it's on the shape? So say if it's on the vertex of an image. And then what is always going to be consistent? So looking at, experiment with a bunch of different things. What is always the same about the pre-image and the image? And then what do you notice about the corresponding sides? So just specifically on the sides, and pull out the measure tool when you do this. So you'll be able to actually measure the side lengths, look at what your scale factor is, start seeing, okay, what's the relationship going on here? And then also measure the distance from each point to the center of dilation on the image and the pre-image. And again, compare and look to see what you can figure out. All right, so now we're moving more into the construction side of things and what we're talking about here when it comes to dilations. So in a dilation, you're going to connect all points. So if we want to figure out where the center of dilation is, we connect all points on the pre-image and the image together, and we extend it. So you should be able to figure out very quickly which direction you're going to extend in, because you're looking for the point where all of those extensions cross. So it's kind of like you're making 3 rays and you want to know where those rays are going to meet. That would be our center of dilation. So in this case, that blue dot is our center of dilation because all of those red lines pass through it. To figure out scale factor, you can pull out your ruler, or sometimes we can do this with compass. We'll figure out how to do this without a ruler later. But we measure the distance from the center of dilation. So in the case of the yellow triangle, it's 22 centimeters from the center of dilation. The blue one is 11. Now our actual scale factor. So scale factor is measured as image over pre-image. So kind of what happened versus how it started. That's where you get your scale factor from. So in our case, we're saying that the yellow triangle is the image and the blue one is the pre-image. Dividing those, you get 2. So the scale factor in this case was 2. Construction. I did a video of this on YouTube. I will have that posted in Schoology. Check it out, and I want you to actually try and do this yourself as well. So here are the steps that you need. So you're going to have your picture, your whatever your shape is. I recommend doing a triangle. If you want to do a quadrilateral, go do a quadrilateral, and a center of dilation. You connect all the points to the center of dilation, extend it. You figure out what your scale factor is. You measure the distance from each point on the shape to the center of dilation, multiply by the scale factor, mark your new point in. And then voila, you have your image. Make sure you label it correctly so you're using prime points and so on. Again, the YouTube video is going to be the true demonstration for this, so you can kind of see the steps, how to do it, what it should look like, and so on. So once you've watched the YouTube video, I want you to do one more try of a dilation on your own and maybe change the scale factor. So in the video, it's a scale factor of 2. Try maybe doing a scale factor of 3, or say like a half or a third or something like that, and apply the same steps. So that's how you'll know if you've truly got it or not. Don't just copy exactly what I did. Do something a little bit different. Change what the shape looks like as well. All right, so say we're given these 2 squares. We can figure out scale factor based on some of the information that is given to us. So for example, one shape is the dilation of another, figure out the scale factor. So if A dilates to become B, what is the scale factor? So B is the image, A is the pre-image. We would take the piece of information we're given, that is 1 side length, and we're going to use that to figure out scale factor. So think about it in your heads, what should it be? So scale factor, if A is going to be, 3 is going to multiply by some scale factor, so this is like the equation we would set up, to become 12. So if 3k equals 12, to get k on its own, we would divide both sides by 3. and we would get k is 4, right? So scale factor of 4. If it was going the other way around, so b was going down to a, then we would flip the equation around. We would say 12 times a scale factor is 3, so the scale factor must be 1/4. So if it's going up, scale factor is 4. And remember, any number bigger than 1, so if scale factor is greater than 1, the shape is getting larger. If the scale factor is between 0 and 1, it is getting smaller. So it is a reduction in size. So enlargements and reductions. Okay, that brings us to the end of today. What do we got? Dilation. It is the increase or decrease in the size of a shape, but where the proportions are retained. So it's the same properties in the pre-image and image. If shapes are similar, that means that a dilation has occurred. So you can have a translation, rotation, reflection. It doesn't change the shape. If you throw a dilation in there, you will get similar figures. And what's true in similar figures? The angles are all the same. The side lengths are proportional based on a scale factor. How can I tell if a dilation is making the shape larger or smaller? We look at the scale factor. If the scale factor is greater than 1, it makes it bigger. If it's between 0 and 1, it makes it smaller. If it's equal to 1, it stays the same. And you can think of that as percentages. So when we zoom, 100% zoom is the original size of the shape. If you go 200, you've doubled the size. If you go 50%, you've cut it in half. So like that's another way to think about it. How do I determine scale factor? You look at the image and divide by the pre-image. And things you can do, you can divide side lengths. So you can tell from side lengths if you divide corresponding side lengths. So we'll add that in too. So remember, in the same position. Or you can do distance from the center of dilation. So that was the example where we pulled out that ruler and saw that, okay, the length from the image to the center of dilation was 22 and the pre-image was 11. So it must have been a scale factor of 2 kind of thing. For tonight, I've assigned you 4 Khan Academies. This will, keep you working on the different aspects of dilations from a coordinate perspective. There's not really much construction we can do on Khan Academy. And then the other part was I want you to construct one dilation on your own. So watch the YouTube video that goes with this lesson and then do at least one construction on your own. I would obviously do more to practice and study and so on. All right, guys, let me know if you have any questions and I will see you soon.